Hello guys and girls, and welcome back to my video where today I'm going to be discussing some algorithms with you. So the first algorithm I'm going to be discussing is the int fast. So let's write it here. So this is called int fast find. And it runs in, the parameters it contains is a vector that contains some doubles. Vector, which contains a double. I already wrote that wrong, and I can't erase it. Let's see here, that's doubles. And you need a key. So I'm just going to do double key because that's what you're finding. From that point, we need to understand what we need. So the problem says, given a sorted array of n comparable items, A, and a search value key, return the position array index of key in A. If it returns present, it returns it, and if it does not exist, it returns to -1. So your algorithm must run in log of k times, where k is the location of keys in A. If it doesn't exist, it runs in log of n, meaning it searched through all items. So let's think about this problem in a way. So what do we know? What algorithm do we know that runs in log of n? Worst case. Well, yeah, the binary search. So what would the binary search also do? It returns, if you give it a sorted array of items of n, it returns to you the location of the index, and if it doesn't exist, it returns you a -1. So do you kind of get what I'm trying to say here?
I mean, you just described binary search.
Yeah, but like, what I'm trying to say here is that you're going to be implementing binary search. So
Yeah, but on the test, the professor said, "Oh, that's not the only thing that you need." Like he added like a little hint besides this.
yeah, I know. Yeah, so you're going to be implementing binary search. So what I'm trying to say is, based on the runtime, you're going to be implementing binary search. Because, worst case, what would be the worst case for binary search? Log of n. Now, we want to make it faster. So, must run in order of log of k. So, what this means is, we want to search a specific area. We don't want to look at every single item. Because let's say this is our list. 1 through 1,000. If we looked at it normally in a binary search, it's going to take ages to find it. Because you have to go from the middle to the middle over here, to the middle over here, to the middle over here. You're going to be going through the whole list until you find it. So, a way that you could do this is by having an exponential or exponent search. So what I... Yeah, it's not something that you're supposed to be taught. It's something that you should, like, visualize. So, let's say I want to find an item from this, from, let's say, what this is. Let's say I want to find the item 500. I have to look through the whole list. Okay, not 500. That's okay. Okay, that's bad. Let's say 501. Do you guys know why it's not 500 in this case? What would be the runtime of 500?
It'd be constant, right? Because it checked the middle. It was the middle.
Yep, it'll be a fast search. That's why. So I'm changing it to 501 because it'll have to look through the whole list again until it finds its midpoint. Unless you have some cases where like, oh, check end and start as well rather than mid. Because you can check start, end, mid, and check if that's your key that you're looking for. So right now, let's say I want to find 500. How you would do this is by checking the key that you're looking for. So you have this key, and your key is 500. So what I recommend is that you iterate through an exponent.
Powers separating by powers of 10 or what?
What do you mean?
Like have it cut it up into pieces, but like have one be like 10 elements together, one be hundreds of elements together, one be thousands of elements together, and so on, and you see if it's in the front or not early on.
So you're grouping these things up by tens only, correct?
Yeah. What would be the way to do it?
I'll need to talk to Dr. Scholler about that implementation because my implementation is differently. I don't go by tens. I go by bits. You know how binary works, like
yeah, 2 to the power of whatever.
Yeah, 2 to the power of n. So I'll just iterate through my whole list. So, for example, 2 to the power of 1, I check my first, like, 1, 2, and check if the key is less than 2. If not, I increment to key less than 4, and keep incrementing until I hit, let's say this is, let's say this is, I believe, let me calculate.
Did you out of bound with that?
So you're giving this list, right? The main reason you're not going out of bound is because n here is the size of your list. So you're gonna be checking, hey, is 2 to the n bigger than the number I'm looking for? So that's one of the conditions you need to check, like, is this 2 to the n bigger than my size? I'll be remaking videos, by the way, because I'm like, just to make sure I'm explaining everything correctly for future references. So you keep increasing your exponent by 2 until you hit the size. If you can't find it within the range that you're given, like let's say you're given 1001 for your key. If you can't find it, then just don't look for it. And keys less than. I want to know if your method would work as well. I think it does, by multiplying by 10 each time, and then you
It's all about making windows, right?
Yeah, it's all about making windows. So how I do mine is I create a window. So I have this list. I iterate through, let's say 501, and I believe 225 to 128. What's the exponent for that one? 2 to the power 128 times 2, 220. Oh god, stop it. Stop it, stop it, stop it. And then multiply by 2. Because I got 2 to the power of something gives me 500. 512. 512. So what I do is this is gonna be my end, and my start is gonna be my start. So this is gonna be my end. My start is gonna be 520 divided by 2, because it's gonna be within these ranges that I'm gonna be searching for. Does that make sense? But honestly, you can create windows. For example, let's say I look at these 10 elements, these 10 elements, these 10 elements. So I keep increasing it to a certain amount. So let me erase this. I keep increasing it to a certain amount. So there's gonna be 10. Wouldn't this be a little bit slow to create these windows though? Because you have to look for every item. I mean, it could work. I'll have to look at the runtime for it. Because you're first iterating through the whole list, checking where that window is until your 50th, because 500 times 10 and then it's within the range of 510. Like this, right? So this is going to be the window that you created based on the power of 10.
And then you run binary search on that one, though.
Yes. Yeah, so you're creating these windows so you can search through them. Makes it faster. All right, let me look at this. All right, let's see. Would this work? Start at further index if matches. Double the index until value is found or you end. So that's what I'm kind of saying. Let me see what your full name is.
Rene?
There it is. I'm horrible with names, but yeah, that's kind of what I'm kind of saying. So you see how it's double the index until values is found or you end. So, but what it means by double is basically you're incrementing it. Wait, did my thing go to this side, to this window? Okay, no. That's just me streaming it for you guys. Oh, have you guys not been able to see the stream? Like
I've been watching it.
when I'm typing the big whiteboard.
Yeah.
Like this.
Yeah.
Okay.
Oh, yeah.
Well, you guys were seeing it from a PowerPoint. That's why. But yes, basically what I mean by doubling by 2, because you see how I said 2 to the power of something gives me, I'm not going to do the math here, gives me 512. And then I divided by 2 to get my starting point. So right here, I search from, let's see, what items are these? 256 through 512. And within those ranges, I can find 501. Does that make sense in general?
Yeah.
Yeah.
Alright. Now program it. Why couldn't you guys get it in the exam? It's pretty simple, right?
Yeah, but like, I looked at it for like 15 minutes and then I just gave up.
Yeah, no problem. No worries. I forgot to teach you guys this. But overall, it's just a very simple algorithm. So, let me write it down for you guys. So, pen right here. What's the color of this pen? So, just find the range. Find the range, which meaning you just increase your... If you can't find it within a small location, then just increment it by 2. So you can do something like this. 2 times equals 2. So you can increment it, but have your first variable be initialized to 1. So find the range that you want to be working with. And from that point, what are you going to do with that range? You're going to put in... Huh?
You have to check if it's equal to key.
Mm,
If it's like less than the key.
yes, if it's less than the key. But that's when you already found the range. You already know that the exponent value that you have is greater than the key, so you can look back. So your start is going to be 2 to the power of n divided by 2, and your last, or I mean, there's your start, right? And your n would be 2 to the power of n. Now, once you have that range, you're going to implement it into your binary search, and you just start searching for it. It's that simple. And then what happens if you don't find it? What's the worst case if you don't find it?
It turns into n.
Yep. Because you looked at every item, and you just return -1. You can't find
That's
it.
another thing that threw me off from the test. He was like, hey, find it in log k if it exists, and then find it in log n if it doesn't exist. And it's like, how am I going to find it in log n if I already searched through the whole thing to see if it was log k?
Yeah. It's kind of basically like this. So it's kind of like this. You know how I said 500? This would be like immediate response, because it is the center of the whole list. All right, so we get that problem now, right, guys? All right. Any questions on it? All right.
Question.
What's your question?
Can we put all 3 functions in like one C++ file, or does it have to be separate?
You can put it in 1. Alright. So the second one that I don't have my notes on. Given a sorted array of n comparable items, create a binary search tree from items in A, which length is h divided by h is less than or equal to log of 2 of n. Your algorithm must create the tree in O(n). So what does this mean? What does this mean, guys? Man, now I really wish I had my laptop for this one, because that's where I have my notes on it. Let's see here. We know what a binary search tree is. So if you don't know what a binary search tree is, it's just mostly just a tree of nodes. So you just have them. So that's just going to be your tree of nodes that you have. Similar to how you did your linked list homework. You're just going to be connecting them. I don't know
Like
if...
I said, left and right nodes.
Yeah.
And it doesn't have to be nothing like recursive or nothing like that. We can do this iteratively, right?
You could. I believe you can do this iteratively. I also believe, yeah, Dr. Schweller. This man. He has some given code to you guys, by the way, for binary search tree. Did he do this in class with you guys? Yeah, so you guys get the general gist of it. So you can do this recursively. which is like insert X into a given tree. Okay. And I believe, let me double check this.
Oh yeah, he has a binary search tree header class.
Yeah.
Which has insert and print. Just to test them out.
Yeah, let me read over his code real quick, just so I can like memorize.
Yeah, it's on CS33, week 213 Wednesday, PST.
Oh, PST.
Okay. So does this man... So it must run in OFN when creating a tree. The given thing is height, which... Did this man implemented in log of 8n? Which has a height... Alright, let me make sure I'm gonna explain this correctly to you guys. So... Well, what do you do in a binary tree? So let's say I input 8. Where would 8 go?
What's the root size?
What do you mean?
What's the root value?
Wait, what? Can you repeat that?
Because you're saying where we're gonna put 8 in the node tree, right?
Yeah.
Well, if it's lower than the root, it's gonna go to the left. If it's higher than the root,
Oh, but like there's a new tree. We're creating the tree here.
oh,
So what?
that becomes a root.
Yeah. That's what I'm like. We have no trees, so this becomes your 8. Now, let's say I add 100. Where would that go?
On the right.
Right.
And let's say I had 101. Where would that go?
To the right of 100.
To the right of 100. And let's say I have 99. Where would that go?
Left of 100.
Alright.
Still a subtree of 100.
So right now what I'm trying to do is explain to you guys. You probably just know what binary tree is. I mean, you know the gist of it. But I'm just trying to re-explain it. So basically, let's say I add a 1. It goes here, right? Let's say I add a 2. Where would it go?
The right of 1.
Right of 1. Now, let's say I add a negative 1. Where would that go?
Left of 1.
The left of 1.
Yeah. So you guys get the gist of it, okay?
Yeah, I know what binary search tree is, but what's the height h of log 2n? What do you want me to do there?
So that's just the height of the tree.
Oh.
I believe so. Let me see. You know, I might need to remake this video because I don't have my notes on me. They're in my other room, and I can't walk to it. So given a sort of a incompatible items, create a binary tree. Your algorithm must create the tree in n times. What does this mean in a way? Because you can create a tree in n time. O of n. Oh, but it's sorted. Huh. I feel like you would, if it's sorted, you would start in the middle and just start placing them.
Otherwise, it's just a regular binary search tree, right?
Yeah. Man, I need to go get my laptop. So let me pause recording right now. Let me see. How do I pause here? I'm just gonna stop recording.